Record. All right, recording is rolling. So welcome to class, Tuesday, January 18th, back from a 3-day weekend. We have a nice short 4-day week going on here. So, I have a new quiz for you guys. Do you guys see attached to the right side of your desk, click to the right side, is a page that looks like this half page. It's got a tuning fork on it, bunch of questions. So let's have this, it'll be open notes take home quiz, just like we've been doing for a long time in here. So open notes take home quiz. Let's have this due coming back from this next weekend. So Monday, January 24th, right? So I'll pick this up on Monday. You guys know that your chapter 14, 15 homework, I'm gonna pick up this coming Friday. A lot of you guys have already turned this in because I've gone over all the main problems, but if you wanna hold on to that, just do by this Friday. I do have a couple of starter questions here that are pretty similar to some of these quiz questions. So go back and recap how to do these. We'll do a Kahoot later today. We won't have time for the sound one, but we'll do waves, and then we'll have a few spare minutes in the class. We'll go back and recap a Doppler equation with you guys, which also shows up on the quiz. And tomorrow we'll do a lab that involves some tuning forks and speed of sound. Speaking of which, tuning forks. I did want to break out this box of tuning forks, which is going to break out tomorrow anyway, because, well, there's a picture of a tuning fork on your guys' quiz. So if you're looking at that, what is a tuning fork? You guys see these different forks? Oh, I can hit them with this hammer. These correspond to different musical notes. The letters say, these would be like musical keys, right? Musical notes, C, D, E, F, G, A, B, C. And they have numbers stamped on them. Like, for example, this G says 384. What do you guys think? What units go with that? That's 384 what? Hertz. Hertz. Yeah, that is hertz. 384 hertz. Tell you guys what too. This is I don't know if this is like some weird set of tuning forks or what the deal is, but these aren't exactly aligned to the main standard. Like for example, A note is usually defined as 440 hertz, but there are other standards, and this one follows some different standard because it says 426.6. So they're off a little bit, but that's okay. Pretty close. Hey, let me check a couple of these so you guys can hear these. Here, I'll check the one that I pulled. So 384 hertz. What does that sound like? Ooh, I feel like a dominant note there. What do you think would happen if I pick one of the shorter tuning forks, like this 512 hertz? See, can be higher or lower note. Ooh, that's a real high pitch there. What if I pick one, or pick the low C? So this is also C, just maybe like an octave down. Octave down actually has half the frequency. So this is 512 hertz. This is 256 hertz. Ooh, so much lower sound there. Okay. Here's someday I'll show you guys the formula that relates musical notes to each other. But yeah, maybe tomorrow. So got those. So let's tackle these couple of starter questions here. Which again, how about this? These questions are things that I've gone over in class enough that if you've taken really good notes and paid real close attention and thought pretty deeply on these, you could apply some critical thinking and figure out each one of these. Yeah, we'll take you guys through these anyway. Okay. So these are pretty similar to some quiz questions. Let's say you have a pendulum swings back and forth, and it's this length, 0.6 meters. Now you guys know that that's 60 centimeters. Okay, so that's just more than half the meter stick. Okay, so maybe it looks about like in a picture. So 60 centimeters swinging back and forth. Hey, I wonder if this guy was standing out on the sidewalk, what would the time period for that be? Ignore this time period. We'll take a look at that in a moment. But what if you're just like standing out on the sidewalk on Earth? Do you guys remember how there's a poster for this hanging right up there? Time period equals 2 pi times the square root of length divided by gravity field. This is also the answer to your guys' last lab. So what happens if you feed this number in for length? So I'm going to put in, go ahead and write this down, 2 pi times the square root of, okay, so 0.60 meters. So that's 60 centimeters. And then for G, well, I'll use 10 meters per second squared. If you want to be more precise, 9.8 is fine too, maybe be better, but just do that. See what we get. What's 2 pi times the square root of 0.60 over 10? I'm looking at, remember this refers to time period, 1.54. What's the unit? What, that's 1.54 what? Seconds. Yeah, because time period, right? So take about a second and a half to swing back and forth. 1.54 seconds. Okay. Okay. Now let's go back to my starter question. Oh, I said time period is 1.35 seconds. Yeah, that looks like a swing back and forth too fast, right? That's too small a time period. Right? Almost like gravity's been altered. Hey, this guy's in an elevator, isn't he? Guys, which way? The fact that time period is too small. Which way is this elevator accelerating? Is it accelerating up or accelerating down? Up. It has to be accelerating upward because it's. Imagine if you're standing in there, you would perceive a gravity field that was stronger than it was on Earth. Of course, there's a normal force from the floor divided by your mass. Okay? There's some kind of like increased artificial gravity field, sort of, okay? Which is making the swing back and forth too fast. See, if you pump up this g, doesn't that make this fraction smaller, which would make time period smaller, like swing back and forth too fast. So it should be doing something like this, swing, swing, swing. It's actually doing something like this. It's kind of exaggerated, but it's what they do. So what would be the upward acceleration of the elevator to make these numbers play out exactly like that? Okay. Remember, if the acceleration is 0, if the elevator is either at rest or moving at constant velocity, then the time period should have been 1.54 seconds, but it's not. It's too short. Okay. Well, now here's where critical thinking kicks in. Can you guys think how to modify maybe this expression so that you even could answer this question? Because what you're trying to answer, what's the acceleration of the elevator? Well, there's nothing, no clear variable to like solve for A. But maybe G is kind of close. Maybe think of it sort of this way, like, if I plug in this L and this T, I could back solve what the artificial G is, sort of like that. Okay, here's where I'm going with this. We're going to modify it this way. The time period is equal to 2 pi times the square root of L divided by, okay, so this looks the same so far. Instead of G, do you guys remember artificial gravity in an elevator? This goes way back to fall semester. It's like G plus or minus A. You guys remember that? Okay. That's what we're going to use. Okay. So if the elevator is accelerating, then the artificial gravity inside would be like G plus or minus A, where G is like true Earth gravity, 2 meters per second squared. Okay. Let's do a thought experiment. See if this actually works. Does it check out? What if, for example, let's go the opposite way, sort of a counterexample to this one. What if this elevator was in pure free fall, just like you cut this cable, this guy's pure free fall all the way down? What gravity field does this guy perceive while he's in free fall? How about 0 meters per second squared? Wouldn't you just be floating around like an astronaut? Right? You guys follow that? Okay. And if that's true, wouldn't that be like G minus G? Right? Because you'd be accelerating down at the rate of G. This A would be G and it'd be down. G minus G, that would be 0, right? Okay. Now here's where things get a little tricky. I want to see if you guys can get this one. What is some length, for example, 60 centimeters, divided by 0? What is anything divided by 0? 0. Careful. Undefined, right? This is one of the tricks that one of the things that everybody stumbles over that. So that's why I'm asking you this, right? That's why we're here. Okay, guys, what is 0.60 meters, 60 centimeters, divided by 0? It says error divided by 0. What if you don't exactly divide by 0? What if you divide by something really, really close to 0, like 0.00001, something crazy, right? Well, that's just a really, really big number, just crazy big number. Okay, so on a graph, this would be like a vertical asymptote, and it basically blows up to infinity. Okay. Well, if that's true, so if you're in pure free fall, A is equal to G, so G minus G is 0. Divide by 0, this square root blows up to infinity. So time would be infinite. It would take an infinite amount of time for that pendulum to swing back and forth. That's to say, it would not be swinging. It would just be kind of hammered, right? You pull it back, say 30 degrees, go, and then you're in free fall, and it just hangs out right there. It takes forever to swing back and forth because it's not swinging. That makes sense. If you're an astronaut floating around, it just, right, there is no gravity field for a pendulum to swing in. Okay, so that checks out. But we're going the other way. reason I'm taking you guys through this whole process is because I want you guys to think really deeply about this. I mean, this is one of the things I want you guys to get out of a class like this is to think really deeply about how processes work, how variables play off each other. If I tweak this way, how does that affect something else? Right? That's something you should get out of a class like this. So we're gonna not do minus, we're gonna do plus because it's accelerating upward. So it's like an increased gravity field strength. And we're solving for what is this acceleration. So I'm gonna plug in this time. 1.35 seconds is the recorded time back and forth. That takes 1.35 seconds to do that. That's equal to 2 pi times the square root. Length is 0.60 meters divided by g is 10 meters per second squared plus a, and we're solving for what is that acceleration a, so that all these other numbers play out exactly like that. Okay, guess that? Guys follow that? Okay. And of course, if you're taking notes, then you'll get this quiz question right. So pretty good. So that's all the physics. The rest is just algebra. So now let's just go back to do that. So divide both sides by 2 pi. So 1.35 seconds divided by 2 pi is equal to the square root. Maybe I'll do let's go ahead and square both sides while I'm at it. It's equal to 0.60 meters divided by 10 plus a. Okay. Let's see what all this crazy stuff comes out to. Because I'm just doing a step at a time here. 1.35 squared divided by 2 pi quantity squared. So tiny number, go right there. So 0.04616 square seconds equal to 0.60 meters divided by 10 meters per second squared plus a. Okay. I'm going to take all this denominator stuff and cross multiply it up. Color E, P, take this, cross multiply this up. Actually, while I'm at it, let's go ahead and take the square seconds number and divide it down. Do a double switcheroo. And so 10 meters per second squared plus a that we're solving for is equal to 0.60 meters divided by 0.04616 square seconds. Okay. So look at that, that's meters per second squared. Here's meters per second squared, we're solving for meters per second squared. We got 3 terms that are all the same unit. Good story. What is 0.6? Sorry, yeah, divided by 0.04616. Okay. And then do you see the last algebra step? We're just going to take this 10 and subtract it over. Okay, subtract 10. So minus 10. Yep, the answer is 3. Well, 2.99. Okay, so acceleration is 3 meters per second squared. There you go. Okay. So the elevator actually is doing one of 2 things. It's either moving up faster, faster, faster at this rate, or it might actually be moving down, slowing down also at this rate. Okay. Either of those would be an upward acceleration. Okay. Highest except we did last semester. Okay. Next question has to do with decibels. Now, I did go over this sort of one day, and on the quiz, I threw you guys a formula that you could use to solve this, although it'd be long. But I want you guys sort of a shorter way to solve the question. It's kind of couched like this. So if you have 70 decibels versus 50 decibels, how much louder is 70 compared to 50 in terms of intensity? Okay. So if you go this, so sound and I'll write this out. Sound intensity level, sometimes abbreviated SIL. This is some number of dB, some number of decibels. It's equal to, this is a formula you guys saw last week, 10 times log base 10 of some number of, well, I should say intensity. Okay. So intensity, which is some number of watts per square meter, compared to some base value, which is like 10 to the negative 12 watts per square meter. Okay. Now, I'm not actually going to use that formula to solve this, although you could, but it'd be kind of a long process. Okay. I'm going to do this a little bit different way. Okay. So the actual intensity is, you can take the number of decibels and treat these sort of like power values, right? Like exponents. Okay. But see, these are decibels. So we're going to convert to bells first. Guys, 70 decibels. How many bells is that equivalent to? 700. Other way. 7. Yeah, that's 7 bells. Right? Okay, so if you had 7 bells, yeah, 70 decibels. Okay, because deci is a tenth of something. Okay. 50 decibels, like 5 bells, wouldn't it? Okay. Now, nobody ever talks in terms of bells, but just for this example. Okay. The reason I'm doing that though is because the intensity of 70 dB is proportional to 10 to the power of the number of bells, 10 to the 7. It's not like 1, 2, 3, 4, 5, 6, 7. Okay. Isn't that 10 million and then the watts per square meter? Okay. Versus what's the intensity? Intensity at 50 dB. Well, the 50 dB, that's 5 bells, and 10 to the power of 5, it's like 1, 2, 3, 4, 5. That's 100,000 watts per square meter. Okay, so if you want to know what's the ratios intensities, intensity at 70 dB compared to the intensity at 50 dB, then you're taking the ratio of 10 to the 7 compared to 10 to the 5 watts per square meter. Compare watts per square meter, the units cancel out. Okay. That's, well, if you want to see the number written out, 10 million watts per square meter compared to 100,000 watts per square meter. You guys see that's going to be 10 to the power of 2 or 100. So it's 100 times the intensity. Okay. Right. Okay. The way I asked the question on the quiz, actually, this is probably the most direct way to solve it. I'll make up some other example numbers. Take you guys do this again. What if instead of 50 dB and 70 dB, what if I did something like 40 and 60? Can you guys imagine that? 40 and 60, which is still the difference of 20 dB, right? Just shifted a bit. So 40 versus 6, yeah, 40 versus 60, right? Well, wouldn't that be 4 bells versus 6 bells, right? So there'd still be a difference of 2 bells. And remember how this is going to come together. So be 10 to the 6 compared to 10 to the 4. And 10 to the 6 compared to 10 to the 4. Well, you subtract the exponents, right? 7 minus 5 is 2. But isn't 6 minus 4 also equal to 2? So, hey, if you went from 40 dB to 60 dB, that would also be 100 times the intensity, wouldn't it? For the same reason. Okay. What if you went from 70 to 90? Well, that'd be 7 compared to 9 bells. There'd still be a power difference of 2. So it would still work out to the same math, wouldn't it? Guess that? And then last week I also mentioned earthquakes and the Richter scale is used to measure earthquakes. So same story with earthquakes. If you have a magnitude 5 earthquake versus magnitude 7 earthquake, the magnitude 7 ends up being 100 times the intensity compared to magnitude 5 earthquake on the Richter scale. Yeah. Okay, guys got this? We have Kahoot. Yeah, so you guys got your phones up? Okay, so phones up, ready for a Kahoot. Any questions on this? Okay, just switch my screen over. Let's share screen. Okay, and find a Kahoot. All right, if you're hopping a minute late, then that 7-digit pin should be at the bottom of the screen. All right, and here we go. The time needed for a wave to make one complete cycle is its what? Yeah, time period. Yeah, time period. So that's the time for one complete cycle. Now, if you pick the red one, wavelength, that would be true if it said the distance for one complete cycle. The distance for one cycle is one wavelength. If you pick the green one, then that's actually the reciprocal of the answer because frequency is the reciprocal of time period. Right? So 1 over time period would be in hertz. Sound is an example of yeah, longitudinal wave. Remember, that's a pressure wave. Tomorrow I'll have a lab for you guys where we'll be working with sound waves, like pressure waves like this. We'll set up some standing waves. So it's not transverse, but you can represent a longitudinal wave as a transverse wave. Let me show this to you guys. I'm going to switch to the screen over. And if you pick the yellow one, constructive wave, well, sound waves actually can constructively interfere, so maybe that's not too bad too. But yeah, the best answer is longitudinal wave. Let me switch the screen over and show you guys what these waves look like. So here we go. Actually, tomorrow the experimental setup would be really similar to this. I have one of those tuning forks that I showed you guys over a PVC pipe, ring saying bing. At some point, it'll set a standing wave, but in general, the wave is going to go. Guys, see how it goes? High pressure, low pressure, high pressure, low pressure, high pressure, low pressure. Right? Each of those dots sort of represents an air molecule. Think that way. Right? You get closer together, further apart, closer together, further apart. Right? And then what can you do with this? Well, you can actually represent these longitudinal waves as transverse waves. Now, why would you want to do that? Because longitudinal waves are really hard to draw. You have to sit here like drawing dots all day and then make sure some are much closer together and some further apart. That's really hard to do. Okay. Transverse waves are so much easier to interpret, right? Because you just like whip off a sine curve, right? Easier to draw, easier to read. Okay. So yeah, so look at that tomorrow. Set some longitudinal waves. Tomorrow, what's that? Sound with a tuning fork. Two or more waves, same place, same time. The resulting effect is called interference. You guys remember constructive interference, destructive interference? So you can add the amplitudes together for constructive interference. Interference. Create interference patterns. Pull out that ripple tank the other day. Where can you touch a standing wave on a rope without disturbing the wave? Yeah, at that node, that nodal point doesn't actually move on a standing wave, right? For example, a microwave in your microwave oven. Standing waves can be set up where? Yeah, all the above. Nice. Right. Now, those are different kinds of waves. And so the red and blue ones would be longitudinal waves because those are sound waves. Okay? You can set up standing waves like that, and we'll do that tomorrow. The yellow one, string of a musical instrument, well, that would be a transverse wave. Okay? Probably with a wavelength that's twice the length of the string. Okay? So longitudinal transverse can be standing waves. Either of those categories can be. Bug is jiggling up and down and swimming towards you at the same time compared to the frequency that the bug is emitting waves. The frequency that the waves reaches you, say this guy on the right, experiences what kind of frequency? Yeah, very high frequency. That's the Doppler effect. Did some of those exercises back before the weekend. Okay. Have time at the end of class today. I'll do some more of those with you guys too. Show up on your quiz too. Same scenario, compared to the speed that the bug is emitting waves, the speed of the waves reaching you is what? Yeah, the speed's the same. Right? So remember, once the waves have been released out into the environment, once they're propagating through whatever medium is carrying them, maybe air in this case, or water if it's like a jiggling bug, the speed is just whatever it is through that particular medium. That does not change. But if either the source or the observer are in motion, then the frequency of those waves that hit you can change. So the frequency changes, the speed of the waves does not change. So there's a points about the Doppler effect. Sound of a car horn passes and receives away from you. What happens to the pitch? Meow. Meow. Yeah, that pitch is going to decrease. It's got a decreasing frequency. Doppler effect is a change in observed frequency due to motion of the source or the observer. So the last couple examples, when the car was moving, that would have been the source, motion of the source. The observer's just standing there. Yeah, could be either way. Change in perceived frequency. If you double the frequency of a vibrating object, what happens to its time period? Gets half. Right. So for example, if you had a frequency of 1 hertz, that might be like so that's 1 beat per second. What if you double that frequency? That'd be more like 2 beats per second. Okay, and then the time between each of those beats would be half a second. Okay, which would be the reciprocal, right? So whatever time period does, frequency is the reciprocal of that. And vice versa. During a single period, the distance traveled by a wave is one wavelength. Yeah, so travels one wavelength during one time period. Right? If you divide one wavelength by one time period, you get the wave speed. Child swings back and forth on a playground swing. What if the child stands rather than sits? What happens to the time period? Would decrease. Ooh, got a couple of winners there. Let me switch my screen over and I'll show you guys why. Let's go with this. A couple of swings set up. Vertical line, just dash line, just for reference. Let's get a couple of swings going. Try to make them pretty identical. But let's say it's one on the left. Kid is like sitting down, something like this. Okay. And the one on the right can have them standing. Something like that. Okay. So to swing back and forth, well, let's think about what's sort of like the effective length of this pendulum. Maybe I should go to like the center of mass of the kid. That'd probably be a pretty good estimate of the endpoint. Center mass of this kid might be right there. Center mass of this kid might be like right about there. Right? Now look at the effective lengths of these things. Okay. This pendulum is a really long pendulum. People call it like L naught or L sit. Okay. Versus this length right here. That's a shorter length. Call that L stand. Okay. I see how this is really long. This is pretty short, long, short. Right. And then how does time period relate? Well, time period is equal to 2 pi times the square root of L over G. It's the answer to your guys' last lab. Gravity field's not changing. So there's some kind of square root relationship between the length and the time period. So as the length gets shorter, 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 so does the time period. So the kid on the left, right, like swish, 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 swish. The kid on the right, it's like soo, 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 soo. It's kind of exaggerated, but you guys get the idea. So shorter length, shorter time period. Suppose simple pendulum is suspended in an elevator. We talked about this. When the elevator accelerates upward, what happens to the time period? Yeah, well, for two of you, yeah, just check out your notes from about half hour ago and get the answer right there. So remember, if you're accelerating upward, think what that would feel like if you were inside the elevator. Wouldn't you feel really heavy, kind of like there was increased gravity? Okay, if there's increased gravity, take a look at this poster right here, time period pendulum, 2 pi times square root L over G. Well, it's like you're dividing by a greater denominator. That would decrease the time period, wouldn't it? That's to say the pendulum's going to swing back and forth really fast. So that was a starter question earlier today. There's a question on your guys' quiz. There you go. Observer on the ground hears a sonic boom created by an airplane flying at a speed of what? Yeah, greater than the speed of sound. So that's supersonic. You guys remember started talking about Doppler effect, but then we were saying, well, what if you were actually outpacing the very waves you're sending out? You create like a cone wave type shape, create a sonic boom. So it's supersonic, greater than the speed of sound. Sound wave that has a higher frequency has a wavelength that is what? Yep, short wavelength. So, but if you multiply those two together, wavelength times frequency, that's the wave speed, and that's constant for some particular medium. So, for example, speed of sound in air at some temperature, yeah. Higher frequency, smaller wavelength, lower frequency, longer wavelength. They're inversely related. Wavelength and frequency are. Two waves, same place, same time, exactly in step with each other. Each has an amplitude of 1 meter. What is the resulting amplitude? Think constructive interference. Yeah, 2 meters. Right, so if you're lying crest to crest, it'd be 1 meter plus 1 meter. You just add them up. So I played some demos for you guys about that. Constructive interference. 1 plus 1 is 2. That is the answer to that. Well, did you know, you get to high school, I have to answer 1 plus 1 is 2. Weight on the end of a spring bobs up and down 1 cycle every 2 seconds. What is the time period? So it cycles every 2 seconds. The time period is 2 seconds. Yeah, nice. Right, time period is 2 seconds. Hey, what's the frequency? What's the frequency? Maybe 1 over 2, and that would be hertz, right? 0.5 hertz. So time period is 2 seconds. Frequency is 0.5 hertz. Leaf on a pond oscillates in down 2 cycles per second. What's the frequency? 2 cycles per second. That's called two hertz, right? 2 cycles per second, 2 hertz. That's like, would be 2 hertz right there. Now the time between each of those would be half a second, but the frequency is 2 hertz. Wave travels 10 meters in 2 seconds. What's the wave speed? 5 meters per second. Right? So 10 meters divided by 2 seconds, that's 5 meters per second. And last question. Wave has 2 crests and 2 troughs each second. Think about what that means, what the frequency is. If the wave travels 120 meters in 3 seconds, think about what the speed is. Then what is its wavelength? All right, so you guys probably figure out the frequency was 2 hertz. The wave speed, 120 divided by 3, that came out to 40 meters per second. And then if you divide down the frequency, 40 meters per second divided by 2 hertz comes out to 20 meters, and that would be the wavelength. Yeah, 20 meters. All right. To the podium with the bronze, Luke. With the silver, Kaylee. And the gold, Olivia. All right, nice job, guys. Oh, here, runners up, got Brinley and Needle. All right. So switch back over to the screen here, and I did on the quiz ask a couple of questions about Doppler effects. So let's do some of those. Start off with something kind of basic, and then I'll ask you guys a bit more complicated one. Okay. Say I got a car in motion, left to right, and this guy's honking his horn, bloop, bloop, and sending out these sound waves. But because the car is in motion, it's kind of catching up to the very sound waves that it's sending out. Great, this kind of thing. Okay. I see that. So we got like crust, 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 and on the other side we got like crust, crust. Okay. See a long wavelength, low frequency, short wavelength, high frequency. And let's say there's a guy on the sidewalk here who's washing his car head, kind of towards him. Okay. To give you some numbers, let's say that the speed of sound, we're going to use 343 meters per second, pretty common textbook value. Let's say the speed of the car is 20 meters per second. And let's say that the source frequency, frequency from the car is like, say 200 hertz. Right. What is the frequency observed? Right. This guy is perceiving what? Right. Now, it would have to be more than 200 hertz, right? If 200, I have a tuning fork that's kind of close to that. I should have picked one of these tuning forks. I got 256. I guess that's the biggest tuning fork I have. So there's what 256 sounds like. It's probably pretty close to that. Okay. So this guy here's like burr, burr, or sorry, if the car's going burr, burr, this guy might hear something like burr, burr, a little bit higher frequency. So Doppler equation, we're going to go frequency observed is equal to the frequency of the source, in this case the car, at rest, multiplied by speed of sound plus or minus the speed of the observer divided by speed of sound. I should say velocity, plus or minus the velocity of the source, in this case the car. Okay. Of course, we're all in one dimension here. Hold it. I guess we're solving for this. Okay. And we should know all these other numbers. Okay, so this looks like a pretty straightforward, just plug in type application. The car frequency was 200 hertz. That's if the car had been parked or at rest, or if you're along for the ride, you hear your own car horn, it sounds like 200 hertz. Speed of sound, 343 meters per second. Now, if the observer is just standing there, then we'll have the observer speed is just 0. So like plus 0 on top, never really change anything. But the denominator, 343 meters per second. And then velocity of the car, I said, was 20 meters per second. Okay, now here's where the critical thinking kicks in. Is should this be a plus or a minus down here? I'll walk you guys through how I would figure that out, because I always have to go through this process every time. Well, I know that this guy hears more than 200 hertz, right? The car frequency is 200 hertz. This guy might hear, I don't know, 230, 240, 250, something more than 200. How are you going to get there? Well, you have to take 200 and multiply by something that's greater than 1. And the only way to get there is to subtract on the bottom. If you make the denominator smaller, then this here fraction in parentheses blows up to something greater than 1. If everybody's at rest, 343 is 1. So, okay, so this would do it for us. So what is 200 times 343 over 343 minus 20? I'm looking at 212 hertz. Yep, that looks pretty believable. And it's more than 200, but not that much more. So we'll go with that, 212 hertz. All right. Now, I'm kind of a trickier question for you guys. Trickier question. Say, got a car again. And this car is going at some speed that we don't know, speed of the car. Let's say it's going away from an observer. Still blaring its horn. Send out these sound waves. They could be a crest, 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 something like that. Okay. Oh, some numbers. Let's have speed of sound as 343 meters per second, just like before. Let's have the car horn frequency at rest be, let's say it's same as before, 200 hertz. Of a 200 hertz, something like that. Okay. And let's say that the observed frequency is like 180 hertz, 180 hertz. What is the speed of the car? See if you guys can beat me to the answer on this. So we're going to go frequency observed is equal to the source frequency times a big ol' ratio. So speed of sound, well, plus my speed observer, but that's just going to be 0 because he's just standing there. Okay. Speed of sound plus or minus speed of the car. Okay. What do we know? We know the observed frequency was 180 hertz. That's that number right there. The car at rest, or if you're along for the ride, sounds like 200 hertz. Speed of sound, we're using 343 meters per second. That goes there and there. Okay. Right, and now, okay, now we're up against the critical thinking part, right? One of the reasons that you're sitting in this class right now is to practice thinking abstract like this. Okay. So, should you add or subtract the velocity of the car? Okay. Well, think this. The only way to go from 200 to 180 is to multiply by something less than 1. And 343 over 343 is 1. So how would I make this fraction parentheses less than 1? I have to add on the bottom plus b car. Okay. Right, and that's what we're solving for. Okay. So if you got that far, we're done with the physics, and the rest is algebra. So break out your algebra skills. Maybe divide the 200 down. So 180 compared to 200 is 343 meters per second over 343 meters per second plus v car. Okay, good so far. Okay, then I'm going to do sort of a cross multiplication thing. Okay. I'm going to take this whole denominator and cross multiply it up to the top on the other side. Right? Like cross multiplication. And at the same time, I'm going to take this fraction on the left side and flip and multiply it on the other side. Okay. So I'm doing a big old algebra switch here across that equal sign. Okay. Some old algebra rules. So that means 343 meters per second plus velocity of the car that we're solving for is equal to 343 meters per second multiplied by 200 over 180. Got hertz that cancel out anyway. Okay, guess that? Let me see what all this fun stuff over here is. What is 343 times 200 over 180? It comes out to 381 hertz. Or, no, not hertz. The unit would be meters per second. 343 meters per second plus v car equals that. Okay. And last algebra step, subtract over the speed of sound. So that 381 minus 343. The speed of the car is 38 meters per second. That's how fast the car had to have been going for all those other numbers to play out. That's to say that if the car was, that the horn was honking at 200 hertz, this guy who the car is headed away from perceives 180 hertz. The car had to have been going 38 meters per second for all that to play out like that. So you guys see that question in your quiz? You got to be able to do that yourself, Steve? All right. Well, that is our wrap on today.